Let's look at graphs of exponential and logarithmic function. First, we'll plot a graph of an exponential function. We have y equals e raised to the power of x. There you have it. Let's zoom in a bit. So, this is a graph of an exponential function where we have e raised to the power of x. Now, of course, if you are plotting it, what you will have, for example, would be like when you have negative 2, e raised to the power of negative 2 would be equal to, what would that be? E to the power of negative 2. You know that e is the base of natural log, right? Each 2 3 decimal places is 2.718. Now, I have an e here. E raised to the, I'll use open bracket, minus 2, close bracket, equal 0.135, negative 2.135, looks like about it. What about e to the negative 1? This is 0.135. To the negative 2, you're looking at 0.135, somewhere about there. When you find e to the power of negative 1, what do you get? Let's see. It's clear. E to the power of negative 1, close bracket, equals 0.368, 0.368. So negative 1, you have 0.368. Seems just about right. I expect when you find e to the negative 0.5, it's going to be more than 0.5. So let's try that. E to the negative 0.5. E, let's clear the calculator first. E raised to the power of negative 0.5, close bracket, equal, and you get 0.606. Alright, so that's what would happen if you were plotting it. Now, e to the power of 1, no, of 0 is just e. Let me erase these. E to the power of 0 is just e. Now, let me make the curve a bit thicker so it's easier for you to see. Alright, so this is e raised to the power of x. Suppose you have 2 raised to the power of x, because remember, e is not the only thing you can use. If you have 2 raised to the x, what would that be? That's also an exponential function because you have x in the power. So remember, generally exponential function is written as a number raised to the x, where x is the power. Remember, x squared is not exponential, alright? X must be in the power, and number in the base and x the power. Suppose you plot now 2 raised to the power of x. Let's see what that would be. 2 raised to the x gives you, let's change the color and the thickness so we can see what's going on with it. 2 raised to the x is the red one. Okay, it passes through 1 as well, because 2 raised to the 0, if you should plot it, you get 2 to the 0 will give you 1. What about 3 raised to the x? What would that look like? Let's see. 3 raised to the power of x equals 3 to the x. It's kind of close to the others. So let me make it, say, 6 raised to the x instead of 3 to the x. So I'm going to just erase it and change it to 6 raised to the x. 6 raised to the x, what would it look like? Six raised to the power of x equals. Alright. So let's change the color and the thickness. I'll change it to blue. So the blue curve here represents 6 raised to the power of x. Now notice it goes steeper as you go from left to right, the larger the number is, right? Because it would climb much faster. While 2 to the power of 1 is 2, 6 to the power of 1 is 6. So for each number here, the one for 6 is higher than the one for 2 and 1. 2 raised to the x. Now, here, for the red line, it is 2 raised to the x. For the red curve, we have 2 raised to the x. Alright? 2 raised to the x. The black curve now is e to the x, which is 2.718 for 3 decimal places, raised to the x. Alright? So, the larger the number, the higher the point will be on the positive side. On the negative side, it will be lower. Notice 6 raised to the x is the lowest for any part, for any point here. 6 raised to the x, the blue is at the lowest point, and the red, 2 to the x, is at the highest point. Because, of course, having 6 raised to a negative number is the same as 1 over 6. Having 2 raised to a negative number, negative 1 is the same as 1 over 2. So, 2 to the negative 1 is a half. 6 to the negative 1 is 1/6. And 1/6 is smaller than a half. So, the blue line is lower. But on the right, if you have 2 to the positive 1, it's 2, and 6 to the positive 1, it is 6. So, the blue line for 6 would be higher on the right hand side of 0, on the positive side. Notice that any number you raise to the x, when you make an exponential function, whatever number you raise to the x, when x is 0, the answer is always 1. Because any number n raised to the 0 gives you an answer of 1. So you have 1 here. Alright? All of them will pass through the number 1 in that case. Alright, now let's do some erasing. And we're going to also look at the logarithmic function. So let me first of all erase these so that I have only e to the x remain. Now, e is the base of natural log. So what we want to plot now is the natural logarithm of x. Alright? So let's plot the natural log of x. ln x. What would it look like? Alright, this is the natural logarithm of x. Let's make the line thicker and let's make the color blue. Alright, so what we have here is the natural log ln of x. Now, notice what happened. There's a mirror line here where the log and the exponent, the natural logarithm of x and the base of natural log raised to the x would be a reflection over that line. Which line is that? Let's see. Y equals x. Alright. This is the line y equals x. So that the straight line here is the line y equals x, which is a green line. So that's the line y equals x. So you can make a note that the exponential graph and the logarithmic graph are reflections of each other over the line y equals x. Alright? Now, what we want to do is make a little modification here. Suppose we change this to y equal negative e to the x. Alright, this is what we have. And then this is negative ln x. Okay. So, the graph for e to the x was originally like this. Now, whatever you have as a positive, it's reflected over the x-axis as negative after that, alright? It would be more like this. Now, here, this is the graph. The black curve is the graph of e, negative e to the x. If I put an e raised to the power of x there, which you can see here, when you have a positive value up here for the e to the x, when you negative what you have the corresponding negative value. Remember, positive up here, negative down here. Positive up here, negative down here. And each positive point is equal distance. Each positive point to the x-axis is equal to the distance of each negative point to the x-axis from below. Alright? So that's what you have there. Now, what we have here is negative e to the x. Let me erase the e to the x here. Negative e to the x and positive e to the x. Now, they would be reflection of each other over the line y equals negative x. Alright? So, that's what you see here. Alright? Now, it's important that you're able to remember what these curves look like. Let me change this back to positive e to the x, and then change this graph back to positive ln x. Alright? So now, here, the e to the x, it gets closer and closer to 0, but we'll never reach it. Right? Here, you would not be able to find e to the x and get a 0 or a negative number. Because remember, if you have a number to the x, say 2 to the x, 2 to the x is not going to result in a negative answer or 0. Because if you have 2 squared, you get 4. 2 to the 3, you get 8. So the larger x is, the larger the answer is. Let's try to make the answer smaller and smaller. This would be 2 to the negative 1, which is half. 2 to the negative 2. Same 1 over 2 squared, which is a quarter. 2 to the negative 5, the same as 1 over 2 to the 5th, which is 1 over 32, and so on. Now, if x is a negative, just like in this case, negative 1, negative 2, negative 5, and you find 2 to the negative 100, it's not going to be 0. Let's use our calculator and find out what 2 to the negative 100 is. Let's clear our calculator first. 2 raised to the power of negative 100. What is it? Well, it's close to 0, even though the calculator rounded it off to 0. If we have 2 raised to the, say, negative 20, we have a very small number. 2 raised to the negative 25, still very small. So the fact is, it gets smaller and smaller and smaller as we go back along the curve. It gets closer and closer to 0, but will not reach 0 and will not cross over into the negative. Alright, no matter what number you make x, it's not going to become, the answer is not going to become 0 nor a negative number. Now, of course, ln, the natural logarithms, right? You will not be able to find the log of 0, nor the log of a negative number, all right? If you say, for example, right, log with a base of e, or even with a base of 10, let's try to find the log of a negative number. Log base 10 of x is equal to, say, 0, right? Log of x is equal to 0. What you're doing is saying 10 raised to the 0 is x. Now, the log of 1 is 0, because this would be 10 to the 0 is 1. So the answer here would be 1. Now we want to try to find the log of a negative number. So first of all, let's try to find the log of 0. If we go from 1 down to 0, and we want to find out what is log 0. Let's say log 0 is a number x. 10 to the x equals 0. 10 to the x is equal to 0. What could x be? If you have 10 to the 1, you get 10. If you have 10 to the 2, you get 100. Alright, so when you increase x, you're going up and up. You want to go down to 0. 10 to the negative 1 is 1/10. 10 to the negative 2 is 1/100th. And so on. Now, no matter what the number is, if it's even 10 to the negative 100, it's still not 0. Right? You would have to argue that you would have to find 10 to the negative infinity to get 0. So you cannot find the log of 0, nor a negative number either. You cannot find the log of a negative number. Right? So, therefore, the curve gets closer and closer to the y-axis, but will never touch it, never reach it. That's the log of x. It gets closer and closer to the y-axis, but it will never reach it. E to the x, or any number to the x, the curve gets closer and closer to the x-axis, but will never reach it. Alright? So you say the x-axis is an asymptote to e to the x. It means e to the x gets closer and closer to it but never touches it. You can say the y-axis is an asymptote to ln x or log x. It means the curve of ln x is closer and closer to the y-axis but will never reach it. Alright? So these are the exponential function, the graph of the exponential function, and the graph of the logarithmic function.